Hi, I'm Dante Cusalito. I'm a pre-FROSH aeronautical engineering student, and for my summer research project, I analyzed the performance of some materials for use in capacitive pressure sensors using COMSOL Multiphysics finite elements simulation software. I worked with Professor Silvana Indriscu and graduate student Mohammed Hassan at the Department of Chemistry and Biomolecular Science. Since undergrad students were not permitted on campus this summer, it was a perfect opportunity to experiment with physics-based simulation in the program COMSOL, as it can all be conducted on a personal PC. So why capacitive pressure sensors? In recent years, capacitive pressure sensors have grown in popularity due to their more desirable properties such as low energy consumption in comparison to piezoresistive pressure sensors. The market has recently found uses for capacitive pressure sensors in wearable devices and other new technology, including for monitoring respiration through barometric pressure. This research aims to find the best performing material among those included in the study for the membrane surface of these sensors. The simulation helped us to calculate the displacement values, which are proportional to the flexibility of the material and the capacitance generated upon applying pressure at the membrane surface. We are trying to find a material that offers some flexibility and enough measurable capacitance. These properties are desirable for applications that involve flexible and wearable electronics. This model here is a quarter of the full sensor, but this geometry was used to reduce computing time in COMSOL. Capacitive pressure sensors work by altering the distance across the dielectric, right here, by application of pressure to the charged membranes seen here. 1 volt is applied between the membrane surface and the surface below it. The gap distance between the membrane and the lower surface is inversely proportional to the capacitance. The simulation results showed that gallium arsenide produces both the highest displacement and largest capacitance. This is by virtue of its low Young's modulus of 85.9 gigapascals, which means it flexes more easily than a stiffer material like silicon, whose displacement map is shown here. As you can see with stiffer materials, the membrane does not displace much, but internal stresses produce an inefficacious result by displacing the steel base instead, around the edges here. While other materials perform moderately well, within the parameters of our testing, gallium arsenide is the definitive choice. Up to the maximum pressure that I simulated, 15,000 pascals, it was the only material to exceed the minimum detectable capacitance by most commercial meters. Considering the limited time frame of a 5-week program and the capabilities of home research, gallium arsenide performed best. But through more expansive simulations, who knows what material will be found. Thanks for listening. If you have any questions, feel free to contact me at cusolidm@clarkson.edu. Thanks.